Hey guys, and welcome back to another video. In this video, we will discuss 1.6 polynomial functions and real zeros, part 1. So this lesson will have two parts. Part 1 will focus on the rational zeros of polynomial functions, and part 2 will focus on the irrational zeros of polynomial functions. Okay, so let's get started. So first, let's define what a real zero is graphically. So graphically, a real zero corresponds to an x-intercept. So if the function crosses the x-axis on the graph of the function, then that corresponds to a real zero, whereas an imaginary zero does not correspond to an x-intercept. So imaginary zero does not correspond to an x. So a function could have an imaginary zero, but we could not tell based off of the graph of the function. Okay, so that leads us to our first theorem of this section, which is the remainder theorem. And essentially, what the remainder theorem says is that if you have a polynomial function, so if you have a polynomial function, say p of x, and a1x plus a0, if you have some polynomial function of this form, then if you divide p of x, if you divide p of x by some factor, say x minus a, then the remainder is simply just p of a. Then the remainder is p of a. Okay, so basically, if you divide some polynomial function by a factor x minus a, the remainder of that division is going to be p of a. Okay, so let's illustrate this with an example. So let's say you have p of x equals 4x to the fifth minus 3x to the fourth plus 2x cubed minus 7x squared plus 9x minus 5. And let's say you divide, and let's say you have to find p of 2. So for this problem, the remainder theorem can be helpful, because although you could just substitute in 2 for each of the x's and then just compute that, it's much easier to use the remainder theorem and instead divide by x minus 2 in this case and then find the remainder. Because what the remainder theorem tells us is that if we divide p of x by x minus 2, because then in this case a is equal to 2, the remainder of that division is going to be exactly p of 2. And so we're going to do just that. And I will use synthetic division. So 2, 4, negative 3, 2, negative 7, 9, negative 5, 4, 8, 5, 10, 12, 4, 17, 54, 43, 86, and then you get 81. So 81 is our remainder for this division, and so that means that p of 2 is equal to 81. Okay, so that is one application of the remainder theorem. Okay, Now let's move on to our next theorem, which is the factor theorem. So what the factor theorem says is that if P of A is equal to 0, then x minus A is a factor of P of x. Okay, so essentially this is saying that if the remainder when dividing by x minus A is 0, then x minus A is a factor of P of x. And I find that to be quite intuitive, right? Because if the remainder is 0, then obviously this is going to be a factor of that. But we'll still illustrate with an example. So let's say we're given some polynomial P of x is equal to x cubed minus 2x squared minus 5x plus 6, and determine if x plus 2 is a factor. Okay, so x plus 2 will be a factor if the remainder is 0. So again, we can just do synthetic division. So this would become negative 2 because this is technically x minus negative 2. And put on the coefficients 1, negative 2, negative 5, 6. Bring down the 1 times negative 2. Add negative 4, 8, add 3, 2 times negative 2, negative 6, add 0. And indeed it's 0, therefore x plus 2 is a factor. So x plus 2 is a factor of P of x. Okay, good. So now let's introduce the next theorem. Okay, so the next theorem is called the rational root theorem. It can also be called the rational root test, but it means the same thing. So essentially what the rational root theorem says is that if you have some polynomial P of x, equal to and it has integer coefficients, then all the rational zeros of P of x, then all rational zeros or rational roots of P of x P over Q, or all rational roots of P of x will have the form P over Q, where P is a factor of A naught and Q is a factor of AN. So it definitely seems like a lot at first, but in essence, it's really simple. All it's saying is that if you have a polynomial function and all the coefficients are integers, then all of the rational zeros of the polynomial, So all like the all the zeros that can be expressed as a fraction will have a form where the numerator of the fraction is a factor of the constant term, and the denominator of the fraction will have the form, or will be a factor of the leading coefficient. So I'm pretty sure an example will make this more clear. So let's do another example. So let's say you have a polynomial p of x equals x to the fourth minus x cubed minus 5x squared minus x minus 6. Okay, so we can use the rational root theorem to find all the possible rational zeros of this polynomial. So in this case, our a0, or our constant term, is negative 6, and our leading coefficient, or an, is just 1, right? So the factors of 6 are 1, 2, 3, and 6, and the factors of 1 are just 1. So p will be a factor of a naught. So these are all possible values for p, and then all possible values for q are just factors of an. So q only has one value, namely 1. And so if we do a0 over an, which is essentially p over q, this will give us plus or minus 1, plus or minus 2, plus minus 3, and plus minus 6. So essentially, you take each of these numbers and put it over this number. But here, plus minus 1 over 1, anything over 1 is just itself. So that's why I didn't write that. But let's say you had more than one number here, you just keep writing all these numbers over those numbers. Okay, but yeah, this is all the possible rational zeros of p of x. And the way you find out which ones are the actual zeros is you just literally test every zero and see which one is a factor. And you can use the factor theorem for that, because if you do the synthetic division and you get a remainder of 0, that means that it's a factor of this, and which means it's also a 0. And so, for example, if we tried, let's say, positive 1, and we did synthetic division with positive 1, coefficients are 1, negative 1, negative 5, negative 1, negative 6. So 1, 0, 0, negative 5. You get negative 12, right? So since negative 12 is not 0, that means that 1 is not a 0, or that means that x minus 1 is not a factor of the polynomial, which means that 1 is not a 0. But if we were to try, let's say, negative 2, so you get negative 2, negative 3, 6, and then now you get 0. So that means that negative 2 is a 0 of the polynomial. And you would just test all the zeros in a similar manner to find out all the rational zeros. Okay, good. So now let's do one more example of this. We have some polynomial p of x, again, is equal to x to the fourth, we'll say 2x to the fourth, minus 4x cubed plus 4x squared minus 36x minus 45. Okay, so our constant term, or a0, is negative 45, and our leading coefficient, or an, is 2. So the factors of 45 are 1, 3, 5, 9, 15, and 45. And the factors of 2 are 1 and 2. So now, like I was saying earlier, you take each of these numbers and put it over each of these numbers. So our total possibilities will be each of these numbers over 1 first. So that just gives us plus minus 1, plus minus 3, plus minus 5, plus minus 9, plus minus 15, plus minus 45. And now you do the same thing, but now you put all of these numbers over 2. So you get plus minus 1 half, plus minus 3 halves, plus minus 5 halves, plus minus 9 halves, plus minus 15 halves, and plus minus 45 halves. So this just shows how there can definitely be a lot of different possibilities. Most of the time, however, some of these fractions will be able to simplify out, and if it is repeated, so for example, if this was 9 over 3 instead of 9 over 2, then this just becomes plus minus 3. But since we already have a plus minus 3 here, you do not have to include it again. So only include every root once and only once. Okay. All right, good. And then, like I demonstrated, you just test each of these roots and see which ones are, let's see which ones are zeros of the polynomial. Okay, good. So now let's move on to our next theorem. And namely, this one is called Descartes' rule of signs. So what this theorem says is that if you have some polynomial, if p of x equals if it has rational coefficients and the constant term is not 0, then the positive real roots is just the number of sign changes in p of x or less than that by an even number. And the number of positive or negative real roots is the number of sign changes in p of negative x or less than that by an even number. Okay, so what Descartes' rule of signs lets us do is see how many possible positive or negative real roots the polynomial can have, and that helps us eliminate a great bunch of the possible rational roots. And basically what this is saying is that to find the possible number of positive real roots, basically look at the number of sign changes in p of x, and then to find the number of negative real roots, you look at the number of sign changes in p of negative x. Okay, good. So now let's do an example. So say you have some polynomial p of x, and it's equal to x to the fourth minus 2x cubed plus x squared plus 2x minus 2. Okay, so notice how it goes from positive, right, because the 1 is positive, to negative. So that's one sign change right there. And then it goes from negative to positive, so that's another sign change. Positive, positive stays the same, but then it goes from positive to negative. That's another sign change. So in total, in p of x, we have 3 sign changes. And so that means that the number of positive real roots is 3. And this is or less than that by an even number. What that means is it can be 3 or less than that by 2. So whatever you get, subtract 2 from that number until you get 1 or 0. So you can have 3 positive real zeros, or you can have 3 minus 2, which is 1. So 3 or 1 positive real zeros. And then if you subtract 2 again, you have negative 1. But negative 1 is not possible, right? That doesn't make any sense. You can't have negative 1 zeros. Okay. And then as for the negatives, you simply just find p of negative x, and that would give us negative x to the fourth stays x to the fourth. Actually, I'll substitute it in, just so you guys can see what I'm talking about. So you have negative x to the fourth minus 2 times negative x cubed plus negative x squared plus 2 times negative x minus 2, right? And so then this becomes negative x to the fourth stays just x to the fourth. Negative x cubed is just negative x cubed, so the negative and negative becomes positive, plus 2x cubed. And then negative x squared just stays positive. That becomes negative, and then you have minus 2. So that's p of negative x. And then you do the same thing that we did for p of x for this new polynomial that we formed. So we went from positive 1 to positive 2, so that's the same. Positive to positive, so it stays the same. Then we went from positive x squared to minus 2x. So that's the sign change right there. And oh, this is supposed to be minus. And then we said minus to minus, so that stays the same. So the number of negative real roots is 1. And if you go less than that by an even number, you get negative 1, which again, like I said, is not possible. But this is very helpful, as we will see. So I'm just going to erase this real quickly so I can continue my example up here. So then now, if we also apply the rational root theorem on this polynomial, we can figure out the possible number of rational roots. So our constant term in this case is negative 2. Our leading coefficient is 1. So factors of that is 1 and 2, and factors of this is just 1. So possible rational roots are just plus minus 1 or plus minus 2. So the way this comes in handy is that we know that we have to have exactly one negative real root, right? The Cauchy science guarantees that. Meaning that negative 1 or negative 2 has to be a root of this polynomial. And so when you're trying to test these numbers now, you have a more structured approach, because now you know that negative 1 or negative 2 has to be a root, right? So we can just start with that. So we'll start with negative 1, and we'll do the thing. So 1, negative 2, 1, 2, negative 2, 1, negative 1, 3, 3, 4, negative 4, negative 2, 2, 0. Boom, it works. So that means that negative 1 is a root of this polynomial. However, that eliminates a bunch of options, right? Because we've already found that negative 1 is a root. But that means we can't have another negative because there's only 1. So that eliminates negative 2. Okay. And it also eliminates negative 1. Again, because you can't have a repeated root because there's only 1. So, and then if we factor this, we get p of x is equal to x plus 1. And then just this polynomial. So x cubed minus 3x squared plus 4x minus 2. And then as for positives, you can have either 3 positive real roots or 1 positive real root. However, we only have 2 total possible positive real roots, right? Meaning that it's either 1, or meaning that it's exactly 1, right? Because we can't have 0. We have to have 3 or 1. So that eliminates the 3 case, and we have to have 1 positive real root. So let's test positive 1. And we can just test it with this polynomial that we just came up with, because if it's a factor of the whole thing, it's also going to be a factor of this new polynomial. And that just helps us lessen the amount of work we have to do. So 1, negative 3, 4, 2, 1. Okay, so 1 doesn't work. So that means that 2 probably should work. So let's try 2 now. So we have 1, -3, 4, and 2. 1, 2, -1, root 2, 2. Okay, so 2 also does not work. However, that does not mean that we don't have a positive root, because remember, these are only the rational roots, right? So we could probably have a positive irrational root, and that would still satisfy this constraint. But essentially, the cardinal rule of sign just helps to eliminate the possibilities when trying to figure out the possible rational roots. Okay, good. And then that brings us to our final theorem for this lecture, which is the upper and lower bounds theorem. So we have the upper and lower bound theorem. Okay. So what this says is let f of x let f of x be a polynomial with real coefficients and a positive leading coefficient. Okay, so f of x is a polynomial with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division so c is an upper bound if the last row is positive, or if the last row is non-negative, and c is positive. And then c is a lower bound if the last row alternates signs and c is negative. Okay, so what does this mean? Let me explain. So let's suppose we have some polynomial f of x, right? And it's equal to 4x cubed minus x squared plus 36x minus 9. Okay, so what this is saying is that if you did the cardinal rule of signs and you found all the possible rational coefficients and you found that 1 was an option, right? 1 was a possible rational coefficient, right? So do the synthetic division with this, and let's see, you get 4. You get like 30, right? So clearly 1 is not a 0 of this polynomial. However, 1 is an upper bound, meaning that the 0 has to be less than 1 because 1 is positive, right? So 1 is, in this case, is our c value. So c is positive, right? 1 is positive. And the last row refers to this row right here. It's essentially your new polynomial plus your remainder term. So if that whole row is positive, which it is, then 1 and 1 is positive, which it also is, then that means that C is an upper bound. So 1 is an upper bound. Okay. So that means that all of our zeros that we're going to test after this should be less than 1. Okay. So let's try 1/2. Right? Because 1/2 is less than 1. So 1/2 may work. And if you do the synthetic division, 4, and then 2, 1, 1/2, you get 73 over 2, and then 73 over 4, and you get something positive, right? Because 73 over 4 minus 36 over 4 is something positive. But that's all the information we need, right? So it's definitely not 0, meaning that 1/2 doesn't work. But 1/2 is positive, so our C is positive. Our bottom row are all positive, and so that means that 1/2 is also an upper bound. So now all of our zeros that we should test should be less than 1/2. So the 0 for f of x is less than 1/2. So okay, let's try 1/4. So if we try 1/4, we get 4 minus 1, 36, 9, 1, 0, get positive 9, and indeed this works. So this just shows, it just like helps eliminate even more of the options. So it just like helps make the work more efficient. But yeah, that is all the theorems for part 1. So these are all the theorems that you need to know to find the rational zeros of a polynomial function. And if you guys are interested in seeing the proofs for any of these theorems, just let me know in the comments down below. But other than that, I'll see you guys in the next video. I hope you enjoyed. Make sure to hit the like and subscribe button. See you guys next time.